Okay, continuing on with our one-dimensional motion analysis. Number 28, a person competing in a dog agility competition calls to their dog that's 40 meters away. The dog was lying down and then sprints to the owner as soon as it hears its name called, accelerating the entire way. The dog reaches the owner 5 seconds after the person started to call their dog. What was the dog's acceleration rate? So this is a problem where it's not necessarily quite so obvious how you can take this complex scenario and break it down into parts. You know, when a ball's in free fall, a lot of times the ways that you can break those problems down kind of suggests itself pretty naturally, analyzing up to the peak, down from the peak, or some other specific landmark like we did in previous problem 27 when the ball was 15 meters above the water. Well, a problem like this isn't necessarily so obvious, but if we make a simple little sketch, I'm not even going to attempt to make a dog. No one's going to win with my attempt at drawing a dog, so it's going to be a person calling to a box. So this one can be analyzed by breaking it down into smaller segments, by analyzing the sound of your voice, because the sound waves are going to travel down to the dog, and then the dog's going to come back. So while it might not be so obvious, this is the way we can break this one down. And if you look at the wording of it, you're told the dog accelerates the entire way. So we're going to deal with that in a little bit. What was the dog's acceleration rate? So what we directly care about is what the dog's doing coming back to you. And one of the values given to us, the dog reaches the owner 5 seconds after the person started to call their dog. So this is similar to the bowling alley problem that we did in the very beginning of this unit, where the ball was rolled down at a constant velocity, hit the pins, and the sound waves of the hit pins coming back to you, we broke the problem apart that way. So this is really the same type of problem. So in this one here, we're going to be able to analyze the sound of the owner's voice calling to the dog. So to clear that that's the segment you're going to analyze, the call to the dog. And the sound waves, that's going to be a constant velocity situation. So we can use our simplest equation, d equals vt there. So given information, a quick Google search will tell you that the velocity of, or the speed of sound is 343 meters per second. And that's just a constant velocity. And we know they're 40 meters away. So displacement's 40 meters. So we can find how much time it takes just for your command to reach the dog. And we can use the simple d equals vt here because it's a constant velocity scenario. So divide both sides by v, and that'll isolate time. So if the dog is 40 meters away, and you calling to the dog, the sound waves from your voice are going 343 meters per second. It's going to take, as you can imagine, a very short block of time for your voice to reach the dog. Approximately 0.12 seconds for your voice to reach the dog. And the reason that matters, if you go back to the wording of the problem, it took 5 total seconds from when you called the dog for the dog to get to you. So what we can now do, we know the total time is the time for your voice to go to the dog plus the time for the dog to actually run to you. So we can do this to figure out how much of that 5 seconds was the dog actually traveling. So since it took about 12 hundredths of a second for your voice to reach the dog, out of the 5 seconds, the dog was actually traveling for 4.88 seconds. Now we can use that to analyze the dog sprinting to you. So let's see what we know. The dog was lying down. So from that, we can pull the fact that the initial velocity of the dog was 0. The time for the dog to travel to you wasn't the full 5 seconds because it took about 0.12 seconds for your voice to get to the dog, was 4.88 seconds approximately. And the dog had to go the same 40 meters that your voice traveled. So from here, you can find what we're looking for, the dog's acceleration rate. So this combination of variables sets up for the quadratic. D equals VIT plus 1/2 AT squared. Substitute in the values that we know. And the initial velocity is 0, so that term goes away. Oh, excuse me. I just realized I made a mistake just from, I wasn't thinking there. Acceleration, I just kind of mindlessly put negative 9.8. Dog's not in free fall, luckily. That's not, that's our unknown acceleration, but the time's about 4.88 seconds. So 40 is approximately equal to 11.91 A. Divide both sides by 11.91. And then we'll get the dog's acceleration rate to you. It's approximately 3.4 seconds. 3.4 meters per second squared is the dog's acceleration rate. Okay, looking at number 29. You're standing on a 20-meter cliff, and your friend down below throws a ball straight up in the air to you. When you catch the ball on the way up, it reaches you moving 10 meters per second. How fast was it thrown? And let's say in the process of trying to catch it, part B, you missed the ball when you tried to catch it. How much longer will it take to actually go all the way up to its peak? So I'm going to sketch this. So here's your friend down below. Here's you. And you're 20 meters above them. So they throw the ball up. And a part A is asking you how fast was it thrown. So we're looking for that velocity right there when your friend threw it to you. And when the ball reaches you, 20 meters later, the velocity right then and there is 10 meters per second. So it's still on the way up. So it's still going to continue onward a little bit more to reach the peak. But in terms of what we're looking for, how fast was it thrown? So because the information that's given to us, it involves some combination of from where your friend was up to you, it kind of lends itself to analyzing from the throw up to you. So this is a case of one of those customized segments. It's not whole trip, it's not up to the peak. So given information, final velocity, not ever, but for this segment, up to you, is 10 meters per second. The entire time gravity is pulling down at negative 9.8 meters per second squared. The displacement is 20 meters because that's how high up you are above your friend. And we want to find initial velocity. So we know it's got to be something more than 10 meters per second because your friend throws it with a greater velocity than 10. Gravity's slowing it down on the way up and it slows down to 10 meters per second. So this combination of variables sets up for VF squared equals VI squared plus 2AD. So 10 squared equals unknown initial velocity squared plus 2 times negative 9.8 times the displacement up to you of 20 meters. So 100 equals VI squared. So 100 equals VI squared minus 392. Add 392 to both sides. So the initial velocity squared equals 492. Take the square root of both sides. So the ball was thrown with an initial velocity of about 22.2 meters per second. So that's part A. Now, part B. If you missed the ball when you tried to catch it, how much longer will it take to reach its peak? So really what we've got to figure out here is how much time it takes to reach the peak, how much time it took to reach you, and then just subtract the two, because the question was how much longer will it take to reach the peak if you missed it on the way up. So from throw up to you, we're going to figure out how much time that is. So we're going to work with the same information, but now we want to find time. So we can do VF equals VI plus AT. And again, we're analyzing just up to you, not up to the peak. So final velocity there is not 0. We're not analyzing up to the peak. Final velocity for up to you is 10. So 10 is approximately equal to the final velocity, the initial velocity of 22.2 meters per second, plus the acceleration rate of negative 9.8 times the unknown time. Subtract 22.2 from both sides. So negative 12.2 is approximately equal to negative 9.8 t. Divide both sides by negative 9.8. So the time for the ball, not to get to the peak, but just from the throw to you, is about 1.24 seconds. Now we're going to figure out is how much time it took from the throw to get to the peak. So since this is a different segment, we've got to declare that we're analyzing a different segment. So our given information, the initial velocity, we didn't know it at the start, but we do now, is about 22.2 meters per second. And now that we're analyzing up to the peak, now we can say final velocity is 0. Gravity's pulling down at 9.8 meters per second, or 9.8 meters per second squared. We want to find time. So once again, we're going to use VF equals VI plus AT just for a different segment. So if I subtract 22.2 from both sides, so negative 22.2 is approximately equal to negative 9.8 t. Divide both sides by negative 9.8. So the time to get to the peak is about 2.27 seconds. So again, let's pay attention to the wording of the question. Part B said, if you miss the ball when you tried to catch it, how much longer will it take to reach its peak? Well, the entire time to the peak uninterrupted is 2.27 seconds. It took 1.24 seconds to get to you, and then you just happen to miss it. So all you have to do then for part B to get this answer, take the 2.27 seconds total that it's in the air up to the peak, subtract the 1.24 seconds it took just to get up to you. So it's approximately 1.03 seconds longer to reach the peak. Okay, Raiders, that wraps up these one-dimensional motion problems. If you have any questions, contact me on the Remind app.